so let's continue our lecture today. So, okay, so last time last time I said that I will spend one lecture proving the living property, but I'll leave it to you as an exercise. Okay. I'll leave it to you as an exercise to prove that. Okay. And then, okay, so he said I'll prove the following corollary. Okay. So let gamma of this x hat to x and this gamma check from this. Yeah, I'm not sure how we really pronounce it, but I will just say it's check. Okay. Sorry for the pronunciation. Be connected covering spaces of a connected locally path connected topological space x, and then we let x naught is equal to this x, and then let this x naught hat to be the gamma inverse of x naught image, and then that x naught check to be belongs to the gamma check inverse of x naught. Okay, so if okay, so if this gamma push forward of this pi 1 of x hat, comma x hat, little x naught hat is contained in this gamma check push forward pi 1 x check x naught check, then there exists a unique commutative diagram of covering maps so here you have this x check here, and then you have this gamma hat here, x hat here, and then this is like the gamma here, x here, and then gamma check here with gamma hat of this x hat is equal to x naught check. Moreover, if this gamma push forward of this pi 1 of x hat x0 check and if this gamma push forward of pi 1 x hat comma x naught hat is equal to this gamma check push forward of pi 1 x check comma x naught check. Then this gamma hat is a homeomorphism, and then okay. Okay. Okay, so just let me know that there's a special case. So if this so if x f hat and smooth manifolds, and uh, this gamma and gamma check are smooth covering maps. Then we have that this gamma check is a smooth covering map. Okay. And hence, this gamma check is a D-morphism if okay gamma push forward of pi 1 x check x naught hat is equal to gamma check push forward pi 1 of x check x naught check. Okay. X naught check. Okay. So I'll prove the I'll prove the topological part. So I'll leave the manifold part as an exercise. Okay. So okay. So now let's start our proof. Let's start the proof for the topological part. So here we have x gamma. Okay, so let's start the proof. So the lifting theorem. Okay, so I think okay. Okay, I think I need to prove a lemma before I prove its theorem. Okay. So Okay, so let's call this corollary 10.2.6. Because it's name of this book. Okay. All right. So yeah, sorry. Before we prove that, we shall prove a lemma first. Okay. All right. So let's start with the lemma. So. Okay. So. So let's start the lemma. Okay, so let this x, y, and y hat be connected topological spaces, and then let this phi from x to y be a continuous map, and then let this gamma from y hat to y a covering space, and that this phi hat to be x to y hat be a lifting, okay, of phi. Okay. Okay, so part A, if this phi prime is a lifting of phi that agrees with phi hat at some in X, then this phi hat prime is equal to phi hat. Okay, so let's so this is an argument that's pretty similar to the uniqueness of the path waving property we proved before. Okay, so so let me just start the proof. Okay. Shall I prove part A or part B? Okay, so maybe I won't. So probably won't finish out, but okay, let's start the proof. Oh, the other part B, part C, part D. So so these are the conditions X, Y, and these are the conditions. So and maybe later on I will say part B, part C, part D. Okay. All right. So let's prove part A first. Okay. So for part A, if phi prime we are lifting of phi agree with phi hat at some point in X, then they are equal. Okay. So let's say the proof. So here that the proof says that this phi hat, so phi hat prime, we lifting of phi phi and assume that the set A, okay, so it is the set of X in X such that this phi hat prime of X is equal to this phi of X. Okay. It's not empty. Okay. Okay, so since this X is connected, okay, is suffice to remember for connected space, if we want to show that so basically to show this equal to that, you need to show that this A is the whole space, right? And then remember so for connected space, the only so if you have so if you have a connected space, the only set that is open and closed must be either the empty set or the whole space, because otherwise you will get a separation. It suffices to show that we need to show that this A is like actually entire space. So suffices to show that A is both a closed and open. Okay, so given a point x naught in x, we may choose a neighborhood U of, we may choose a neighborhood U of phi of x naught such that okay, so this U hat being defined as gamma inverse U, which is equal to the union actually here it's like the disjoint union lambda in big gamma, or okay, so I forgot, yeah, U lambda, okay. Where this set U lambda is an open set in this y hat. Okay. And this gamma maps this U lambda homeomorphically onto U for each. Yeah, so this is the this is the definition in the covering space criterion. Okay, so hence there exists unique indices lambda and lambda prime with this phi hat of x naught is in U lambda, and phi hat prime of x naught is in this U lambda prime. Okay. So let's see why this is true. So okay, so we fix a point x naught in x. and then we choose a, okay, so what is, okay. And then we choose a neighborhood U of Cx naught. And then we, yeah, because this, this gamma from y hat to y is a covering space, so we choose a, so we choose a evenly covered set, okay. And then, okay. So, hence there is unique indices. Okay, so why there is unique indices? Because okay. Okay. Oh. Why there is the uniqueness? Because, okay. Because this the hat maps x naught to this x naught is in x, right? X naught is in x. Yeah, and then yeah, we take the point. Yeah, and then this phi hat maps, yeah, as is x naught to the x into some point in y hat, and also we know that it's a projection. It's a lifting, right? So lifting means that you compose with the gamma, and then you get the same thing. So here, this must lies in the pre-image of this gamma given U. Okay, yeah, because x naught is in U. Okay. Oh, wait. Because this phi x naught is okay. Because okay, so what's the reason? So here, okay. Why there is this lambda prime this phi hat x naught is in U lambda. Why? Why there is lambda com? Okay. Yeah. 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 Just by the covering projection. Okay. Yeah, there's nothing to show here. Okay. All right. Anyway, so let's continue. So. Okay, so that is you have this the hat of x naught is equal to this gamma restrict U lambda inverse of phi of x naught, and okay, and we have this phi prime of x naught is equal to the gamma restricted on this u lambda prime inverse of phi of x naught. Okay. And then we set then the set V, which is being defined as phi hat inverse of u lambda intersect this phi hat prime inverse u lambda prime. Okay, so there's a prime here. Oops. Okay, is then a neighborhood of x naught. Okay, so let's see why this V, which is being defined as phi inverse u lambda. Oh, sorry. Phi hat inverse of u lambda. Okay. Because yeah. Okay. Okay. So what? Okay. Okay. It is true because we know that this u lambda and u lambda prime, they are open in y hat, right? Y hat, sorry. And then they wait. Okay, okay. And then this okay, yeah. Wait. And then this phi of okay, yeah, and then this phi of x naught, and then this phi of they contain in these two sets separately, okay. And then you take the inverse of one set, they're open. Because because the coverage because the map phi hat is and phi hat prime, these two maps they are continuous. Okay. Okay, so now wait, what is am I running out of time now? Okay. Okay. So if this x naught is not in the set A, then we have that gamma is not the same as lambda. Sorry, lambda is not the same as lambda prime. So this phi hat of V intersect this phi hat prime of V is equal to the empty set, and hence V is contained in X. Take away A. Okay, so let's see why this is true. So, okay. Wait, why is, yeah, the lambda is not equal to lambda prime. Yes, okay, because, yeah, there it is, right, okay. So, we had y. Okay. What is u? Okay, so why this we had u intersect